Okay, so we said as far as this class goes, what Monte Carlo methods does is it allows us to answer a lot of these statistics and probability questions without doing math. Okay, instead of, I mean, obviously we have to do some math, but without doing a lot of complex analysis, instead we can get approximate answers by drawing samples from distributions. Okay, so so in our course we answer statistics and probability questions by drawing samples from the distribution of interest. Okay, instead of doing mathematical analysis. Okay, so stats, 100A, 100B, you'd say something like the expected value of some distribution x is equal to the integral from negative infinity to infinity of x times the probability distribution of x, or something like this. Okay, or and this could end up being a complex integral to b, right? It could be a difficult integral to calculate. Okay, so the Monte Carlo approach will be to draw, samples from the distribution defined by p of x, okay, and then just calculate the mean of your sample. And basically, the x bar of your sample will be approximately equal to the expected value of x, okay? And as n approaches infinity, then x bar will approach the expected value of x, okay? Assuming if x bar is an unbiased estimator. I got to throw that in there. Okay. Likewise, you could have maybe some other thing. So you could have another function. You could have a function f of x, and maybe you're curious about the expected value of the function of x, okay? So let's say f of x is equal to x squared, okay? Or we might say z is equal to the random variable x squared, okay? And we could say, this is lecture 2. Okay, and if x comes from, let's say, normal distribution 0, 1, then, what is the distribution of z in this case? Right? Okay, and so do we recognize this thing? The chi-squared distribution, 1 degree of freedom, right? So we know from mathematical statistics, or from 100A, we know, or is it 100B? 100B. Okay, so from 100B we know z comes from chi-squared distribution with 1 degree of freedom. Okay, so you know this we already know, but you know you could imagine something more complicated, and we ask, you know, what is the mean? What is the mean of z? Right? What is the expected value? Expected value of z, or what's the expected value of f of x? Okay, and it's not the expected value of x squared is not equal to the expected value of x quantity squared, right? Because if x is the normal distribution and the mean is 0, the expected value is 0, the expected value of the chi-square distribution is not 0, okay? So we know this is not the case. Instead, we would have to do the integral from negative infinity to infinity of f of x times p of x dx, okay? Again, could be complicated. So the Monte Carlo solution is draw x, square x, and then take the mean, I should say draw sample of x. Okay, square your sample, and then mean of, you know, the sample squared. And that will give you an approximate answer. And as your sample size increases, you will get closer and closer to the true value, right? And so this is kind of the Monte Carlo solution or Monte Carlo answer for getting these, for answering these questions. Okay, so this requires that we have the ability to draw random samples from a specified distribution, okay? So we need the ability to draw random values from a specified distribution. Okay. And so we're going to start off with the uniform assumption, okay? Or our first big assumption is that we can draw values from the uniform distribution. Okay, or in other words, we assume that our unif, R from the uniform distribution works, and we have access to it. This used to be this was a topic of great interest and research for a while, and now we're at a point today where we're very happy with our pseudo random number generators. Okay, so you know today we have good PRNGs. Okay, pseudo random number generators. Okay, I'll post a video on PRNGs that it discusses old methods and the most popular method today, which is the Mersenne twister. But Mersenne twister, it's beyond the scope of the course. I don't fully understand how it works. It's like it uses some 624-dimensional hypercube of values that it shifts. I don't quite get it, but we just know that it has passed this battery of tests that says like, yeah, it seems like it's pretty good. Okay, so we're gonna draw values from the uniform distribution. We'll assume that this this works. And if we can get uniform values from the uniform distribution, then we can get values from, we can use it to get values from other distributions, okay? So we can, we will use the values from the uniform to get values from other distributions. And the method that we'll cover today is going to be called the inverse CDF method. So this is our topic for today. So we'll start with kind of just going through maybe some stuff about, I guess, PDFs and whatnot, okay? So let's, we'll start with the normal distribution. Okay, and so we have the PDF, the density function. And for the normal distribution, the density function looks something like this, right? And okay, and as far as the density function goes, we've got the density function, we'll call this f of x, and we know that f of x must be greater than or equal to 0 everywhere. So it's never allowed to be negative. And then the other rule is that the integral from negative infinity to infinity of f of x has to equal 1. And that's pretty much the only rule. And in R, this is basically d norm of x. Okay, so d norm of x will give you the density function. Okay, and then from there we have the CDF. This is the cumulative density. The cumulative density is defined as capital F of x. All right, this is the probability that your random variable x is less than or equal to some value x. And this is defined as the integral from negative infinity to x of your density function, but we have to change the letter, of f of t dt, okay? And for the normal distribution, the let me shift this over. Let me try to get this flat. Okay. All right, so we'll we've got this, and okay, and so this should look something like, okay. All right, my picture is not very good, but I think you know what I'm trying to draw, right? So, you know, it goes down towards negative infinity, it approaches 0, and then as it goes to positive infinity, it approaches the value 1. Okay, and so the CDF maps basically x to the interval 0, 1. And we have something, this is the probability integral I didn't write this theorem name last time, but we've got the probability integral transformation. And basically that says if x is a random variable with CDF f of x, okay, then if you apply this CDF to the random variable f of x, this is equivalent to the uniform distribution 0, 1. Okay, so if you generate a random value from the distribution x, okay, so if we generate a random value from x and plug that value into f of x, okay, we get a value between 0 and 1, and those values will follow the uniform distribution. Okay, and so what is the cumulative density function for the normal distribution in R? You guys know this, right? It's called P norm, right? Okay, and you plug in, what? You didn't know this? You've never used P norm? What? You have, okay. All right, so you've got D norm, it gives you the density. P norm gives you the cumulative density. So if I plugged in P norm of 0, what would I get? What? 0.5, right? P norm 0 is 0.5. Let's see if you guys know this one. P norm of 1.645. 95, right? 0.95. That's why, like, for a 90% confidence interval, because you want the middle 95%, middle 90%, 5% above, 5% below, you get 0.95, right? 1.96, P norm 1.96, what's that? 0.975, right? 0.975, right? Okay. Okay. Okay, so we have this, and then okay, so this is P norm, and let's go to the next one. Here, I'm gonna copy this. I hope this works. This is a terrible picture. I don't know why I'm copying it, but I'm doing it for illustration, right? So we have the inverse CDF, okay? Okay, the inverse CDF is going to be big F inverse. Okay, and we will say this is defined as the minimum value of t where big F of t is greater than u for 0 less than u less than 1, okay? And the inverse transformation, inverse CDF transformation is that we'll say u is uniform on 0 to 1, and this says that if you plug in values generated according to the uniform distribution, and you plug those into the inverse CDF, those values basically come from the distribution of x, okay? So values u generated by uniform 0, 1, okay, plugged into the inverse CDF will produce values that come from the distribution of x. Okay, so if I have the CDF function, so let this be the CDF. Let me okay. Then the inverse CDF inverse will be we take this and then I flip this and I have to rotate this, right? Because that's what an inverse function does. Is it flips it and then it rotates it, or basically does kind of the it flips it across the symmetry axis y equals x, right? So that's what we've done here. So this is our inverse CDF function, and so now our it goes from 0. This is not. How do I? I'm trying to get get my axis drawn correctly. Okay, this looks about right. Okay, 0 to 1, and thus right here, if I plug in 0.5, so this over here is p norm. So if I plug in p norm of 0, I would get 0.5, and over here this would be q norm, and if I plug in 0.5, I would get 0. Okay? And if I plug in q norm 0.025, what would I get? So if I go to 0.025, I would get negative 1.96. No? Yes? I would. Okay? So if I do q norm 0.025, okay, well, negative 1.959964, so close enough to negative 1.96 here, okay? Whereas if I plugged in p norm of negative 1.96, I get 0.025, right? So these are like inverse functions of each other. So p norm is the CDF function, and q norm is the inverse CDF, okay? Which is defined as this thing here. Okay, and so here you plug in a quantile, and it returns the percentile. And here you plug in the percentile, and it returns the quantile. So that's where the P and the Q, those come from the terms percentile and quantile. So you plug in a quantile, and it'll give you the percentile and P norm, and Q norm you plug in the percentile, and it gives you the quantile. The inverse CDF here. Okay. So so basically, the way the inverse CDF thing works is to generate random values from a distribution. First you got to derive the inverse CDF, F inverse. Okay, right now we're kind of cheating by using Q norm. Okay, the truth is that the inverse CDF for the normal distribution is very complex, and it's hard. But you know, right now we're kind of cheating. Okay, and then the next thing is to generate U coming from uniform 0, 1, and then let X be equal to F inverse U. Okay, and then and this will then X basically comes from a distribution defined by the function f of x. Okay, so you know, this is kind of trivial with R. Well, all of these things with functions that are already defined in R, the idea of generating random values is a bit trivial. We would never actually do this in practice because R norm works excellent. You know, any of these R things, right? So we already have R norm to generate to give random normal values. Okay, so we wouldn't actually do this, but you know, we can use R unif and Q norm to get random normal values. Okay, and this is actually kind of what R does. Okay, so R unif generates basically random uniform, and Q norm is the inverse CDF. So we could use random uniform values along with the inverse CDF, and this is what R actually kind of does. Okay. Oh, here's a plot of the of Q norm, right? This is the inverse CDF. So let's say so if I do set seed 1, and I can say U is going to be R unif 10. Right. So here are 10 random values from R unif, and if I plug those in, Q norm of U, I get these values here. Okay, and so these values are random values according to the normal distribution. Okay, and to kind of show you that this is kind of what R is doing, I'm going to go back and set seed 1, and I'm going to just use R's regular random normal function, R norm, and I'll ask for 10 values, okay? And what we see is that this value, the first value it generates, is indeed the same as the first value that I got over here, okay? The next value that I generated using my method, for some reason, disappears, okay? But you can see it's as if R norm is using random uniform values, but only every other one. And I'm not exactly sure why, but you can see that here I have 1.836 and I got, or 0.1836, and I've got the same thing. So every other value is indeed what appears when I do R norm, okay? So it's as if I did, if I subset U by doing repeat the sequence 1, 0 5 times or something, okay? And then I plug this into Q norm, okay? And if I do that, then this is equal to, oops. Okay, I messed something up. Oh, not 1, 0. I needed a. Is it not just true false? Oh, true false. Okay, and those two things would be equivalent, right? So if I generate random uniform values and I plug those into Q norm, I'm effectively getting the same thing as R norm, okay? The truth is that, again, the inverse CDF of the normal distribution is really complicated, and Q norm actually uses a high quality approximation, and you can read all about that. You don't have to, okay? For Q norm, this code is a C translation of this person, Wichura 1988's algorithm, which provides precise results of about up to 16 digits, okay? Which is good enough for our sake. Which is good enough for as far as floating point arithmetic can do, okay? All right, so that's what we have for the normal distribution. Oh, well, I mean, that's just kind of the illustration of all of this stuff for the inverse CDF method. And this can be applied to other things, and you might have to, calculate the inverse CDF yourself, okay? So for example, let's say we've got the exponential distribution. Now we're gonna run out of. All right, I'm gonna go very quickly here, and you can just review your notes if I went too fast, because I've got 10 minutes left, and we've got a little bit more to cover here. Okay, so the PDF for an exponential f of x is defined as lambda e to the negative lambda x for x greater than or equal to 0, okay? And the CDF is defined as f of x is equal to the integral from 0 to x of lambda e to the lambda t dt, again, for x greater than or equal to 0. And thus the inverse CDF can be found this way, is you set f of x equal to u and solve for x. Okay, so f of x, when you integrate this, ends up becoming, I should put this over here, 1 minus e to the negative lambda x. Okay, so we have 1 minus e to the negative lambda x is equal to u. And solving for x, we're going to get x is equal to negative 1 over lambda log of 1 minus u. Okay. 1 minus, if u comes from the uniform, 1 minus u is equivalent to u, and they both come, not equivalent to u, but will also come from the uniform distribution. So a lot of times we'll just say the random variable x can be defined as 1 over lambda log of u. Okay, and this is equivalent to an exponential distribution with parameter lambda. Okay, and so if you wanted to generate values from the exponential distribution, this is a lambda here, you can use the uniform distribution and just take the log of that and multiply that by negative 1 over lambda. And that will give you a uniform, give you an exponential distribution. Okay. I have to cover the discrete case. Okay, so sometimes we have discrete distributions, and we want to generate values from the discrete distribution. Okay, so what we have here is going to be, let's say we've got the probability mass function, okay, is going to be defined as, you've got values of x and the probability that x equals some value x. Maybe we'll just have, we'll keep it simple. We'll say x can take on the values 1, 2, or 3 with probabilities 0.2, 0.5, and 0.3. Okay. Thus, my probability mass function 1, 2, 3, 4 will look something like this. Okay, so there's my probability mass function that says this is the probability of getting each discrete value. The CDF then will look something like this, okay? And we have for x less than 1, the CDF is going to be 0. And then for 1 is less than or equal to x less than or equal less than 2, the CDF is 0.2. And then from 2 to 3, we're at 0.7. And then for 3 and up, we're at 1. Okay, and so our CDF will look like this: 0, 1, 2, 3, 4, 0.5, 6, 7, 8, 9, 1.0. And I'll do this in blue. Okay, and so this goes like this, and then at 1, we come up to here. At 2, we're at 0.7. Okay, and so there is our CDF. All right, is this okay? And so the next thing then is the inverse CDF. Okay, so let me, all right, actually, let me put this here again. And so our x and our CDF, and then 0, 0.2, 0.7, and 1.0 for okay. The inverse CDF, okay, again is defined as the minimum value of t that satisfies that f of t is greater than or equal to u, okay? And so the inverse CDF is going to look like this. So we've got some value u, and the inverse of u is going to be this. And so from 0 to 0.2, it'll produce the value 1. From 0.2 to 0.7, it'll produce the value 2. And from 0.7 to 1, it'll produce the value 3, okay? I'm gonna shrink this down and flip it and rotate this, okay? And so this is kind of what it will look like, except this is not quite right, okay? And the reason for this is because now I have vertical bars in my function, which is not allowed, right? So what it ends up becoming is so if I go from 0 to 1, 2, 3, 4, 5. Straight line here. So if this is 1, basically we start at from 0 to 0.2, it'll produce the value 1, and then at 2, it goes from 0 to 0.7 will produce values of 2, and then lastly values from 0.7 up to 1 will produce values of 3, okay? And that's because of kind of this minimum operator, because the inverse really only needs to worry about mapping values between the range 0 to 1, okay? So this is the inverse CDF. And so again, to generate values here, basically generate u from the uniform, and then you just plug in to the inverse CDF function. And if you do this, you will get values according to the discrete distribution defined here, okay? And you can see that, you know, by looking at this, that indeed 30% of values will be number 3, 50% of values will be number 2, and 20% of values will be number 1 if we're producing uniformly on the interval 0 to 1, okay? So this is the inverse CDF method. This is kind of a basic way to generate values from some random distribution. The trouble here is that it requires you to calculate the inverse CDF function, which sometimes is a difficult thing to do. But if you're able to do it, this is a good way to go. Okay, we'll see you guys on Friday then.